Alright, I'm gonna try to make this video again. Yeah, I haven't seen this stuff in like a year, so I try to make a video. I have to do it again. But so these are the main links that really tell you everything. Some of these are hard to find, and luckily some of the things I had saved links don't even work anymore. So there's a couple little questions I had with the circuit that I was going to have to test and figure out. So, but let's get started on explaining the circuit. Well, this is the technical product information for the LSU 4.9, right? For the oxygen sensor itself, and it shows you a circuit for AWS. I've seen that somewhere before. But there's this is what we're going to be getting into too. It's the Bosch chip, which is a CJ125, which is we'll get to, but that's the little square black chip CJ125 that you can't find the real one. Apparently they don't sell the real one to regular people. I don't know, but all I could find was they're all Chinese knockoffs. But before we get into the schematics of the chip and how it worked, let's look at this. Is the data sheet for the oxygen sensor itself, and this is the circuit to control it. And apparently there's another controller called an AWS as opposed to the CJ125 AWS control box. These are some of the control boxes that are available. Well, this is showing an AWS. So basically you got these connections. These are your wires from your sensor, or your O2 sensor. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, that's right. Now, so you got your heater wires. Your heater is just going to get PWM, temperature controlled, with a PID coding to for your heater side of it, and I'll show you that in a little bit. So that's one section. This is all the sections, right? So you got that section for your heater, and then you've got let me show you this other picture so it'd be easy to show you the sections. So now that's for the sensor itself. Now this is the CJ125 chip. So if you look here, this is the oxygen sensor, and you can section it into two sections. Well, three. We got the heater section, right? And then you got the nurse cell and the pump cell. Now the pump cell is, you're going to be pumping current into it, and by how much current it needs for your comparison cell to stay steady at the target is the output of this sensor, right? Now see, this nurse cell and this pump cell, they're connected. So this is like your pseudo ground. This is your pseudo ground to your VM, and that's going to be 2.5 volts is your 0 point. It's going to be a pseudo ground of 2.5 volts. It's basically, you can consider it your ground. And on either side of that is the nurse cell and the pump cell, and they affect each other. And all your comparison is going to be done off this side, the nurse cell, and then your main output reading is going to be from this side, and how much needs to be pumped into it to keep your comparison correct. Alright, so there's nurse cell, pump cell, heater, and that's main parts of it. Now so your heater, let's start with the heater. Alright, that's not going to be on this. Let's see, where would it be? Let's go back to here. So your heater. So you got to have a what do they call it? A plan for your heater thing, right? So because when you first start up the car, they're assuming there's probably going to be some condensation in this oxygen sensor, and they don't want to, you know, it's got ceramic and shit in it, so they don't want to thermal shock and damage of the sensor ceramic, right? So during the condensation water phase of the heater, power must be limited to rule out thermal shock. Heater voltage during condensation water phase should be less than 2 volts. I've seen most people say 1.5 volts for this section right here. So you're going to run it for 1.5 volts for the condensation water phase, and your max initial value is 8.5 volts. So you're going to jump it up, and then your max ramp rate 0.4 volts a second. So after you basically burn off the condensation, then you go for less than 8.5 volts, and you ramp it up slowly at that rate or less until you get to your target temperature, and which should be no more than 13 volts needed to do that. So, okay, maximum permissible effective heater voltage to reach the operating point. Short time, less than 30 seconds. I don't know what that really means. Continuous, accumulated. I'm not sure what that's trying to say. Maximum system supply voltage, which is basically your battery voltage versus plus your alternator charging voltage. So it's going to be like 13.5 on your car. It's got an alternator running right. And the maximum frequency of the heater control is greater than 20 hertz and less than, or wait, recommended value is greater than 100 hertz, and I think the maximum, that's somewhere else. I'll show you that in a minute what the maximum is, but it's got a maximum frequency also, so it's got to be at least 100 hertz. You're just going to PWM to control the voltage from your straight off the battery voltage. So 1.5 volts for a certain time period, which I have lost what said that time period was supposed to be. I know it's got to be like somewhere around 30 seconds or so, and then you jump up to this voltage or less, and you ramp rate to this voltage or less until you hit the target temperature. Now the temperature sensor is see what the best way to express. So you got to notice that the nominal voltage, which will be what, nominal heater power at 7.5 heat at the thermal equilibrium in air. So you got to realize that this is going to use 7.5 watts normally and up to 15 watts total. So you got to have your heater supply able to do up to 15 watts at a max of you know, with 13.5 volts going through it, 14 volts going through it, at a max of 7.5 or a max of 15 watts. So you got to make sure your MOSFET that you're switching can handle that. Obviously, normally it's going to take about 7.5 volts continuously once it gets all stabilized out, but you just start it and you see how long, you know, you just go until it hits the normal temperature, and then it'll all stable out after that, you know. So these are temperatures just like in the air. So you know it's going to take a little more than that. Nominal heater cold resistance at 4. So it'd be nice to have a circuit to read the ohms of the or the resistance of the heater side to make sure the heater ain't burned out and and is going to work correctly. So if you had a circuit to read the resistance of the heater before you start using it, just to make sure it's like a little diagnostic before it starts, so it ain't burned out or something, that'd be nice to put in your circuit. But either way, yeah, you PWM this with these parameters, and I couldn't find this number again. It's like 30 seconds or something for your burning off your condensation, and I guess you could probably get away with getting around that if you've got a way of knowing if the car's already warm, which the temperature for this thing will tell you. If you just shut it off and walked in a gas station and come back, you don't need to go through this condensation step again, but you'd have to know that, and you go by the temperature. See now, okay, so you got a heater here, right? Now this the nursed, the part that's on the, if we go back to here, the nursed cell is actually doubles as the temperature reader too. This will tell you the temperature, and to do that, to tell the temperature, now here's the circuit for the IC. Now here's your nurse cell. How to do this without being too confusing. Maybe we'll go back to this. Okay, so what you're going to do is the nurse cell itself needs a reference. Oh, okay, reference pump current. Okay, so the nurse cell needs a reference current for it to work. Now, see this cell here, the nurse cell, you see in the 4.2 oxygen sensor, it had a thing with oxygen inside of it, and it compared that to what this pump side was reading, and that's how it made its determination. And what happened was in the 4.2 that side holding real oxygen kind of went bad after a while, and then it didn't have nothing correct to compare it to. So now on the 4.9 they used some kind of silicone thingy to replicate the thing to compare it to. And so it's being replicated by a silicone, a solid state method, instead of having an actual container of oxygen to compare it to. So to make that solid state method work, it has to feed it a 20 micro, or what was it, micros? Yeah, 20 microamps reference into this nurse cell, and then the voltage that occurs because of that is what we're going to be using for comparison, because these two are actually connected and affect each other, even though that's solid state. And so that's going to be used as a comparison to know how much current needs to be pumped into this side, and the amount of current being pumped into this side based off of that comparison is going to make the output of our sensor. So let me explain this here. This right here is a current sense setup with op amps doing current sense, and the current sense is going across. See, I just did this video and I made it badly, so I had to redo it, and I'm getting confused on if I said something already or not. So let me go back here. Okay, this is it. This right here is a 100 ohm laser trimmed. I think it's 100 ohm. It's something like that. I don't remember exactly, and I didn't look it back up. And this is a resistor, a high precision laser trimmed resistor. I'm pretty sure it's 100 ohms, and it's actually located in the plastic wire clip of the oxygen sensor itself. It's like built into that plastic clip. Now this is, you're going to need a 61.9 ohm resistor, possibly, and well, I'll get to that, to for the current sense, and this is what, between those two, the current or the voltage drop across those two, or the current used across these two, is what you're measuring to get your output. But the thing is you're comparing this side, the nurse cell, and that's going to go through a current pump. This is a current pump, pump current control, and that goes through from here and is comparing that to its reference voltage and determine how much the current to pump all the way down here into IA in the beginning of this side, and that current is going to go through these two resistors, the one that's on the oxygen sensor clip and the 61.9, and that current is getting, that's used to make this balance up here, is getting read by this current sense op amp set up right here, and that's your output. So now this is all for somebody that knows microcontrollers and regular, at least regular electronic basics, you know. Now you can ignore most of this crap, because this is how they do their circuit, and it's really bad circuit. It's that these are all the revisions. The red and blue is all the revision stuff and what was added since that. And if you look at the parameters down here, they're not that great. It's not a very precision. It's and if you look at the explanations of certain certain resistors and capacitors used in here, like this one for parasitic loss, and they're accommodating for problems in the circuit by adding these resistors and tweaking it. And that's because they use, see all these little switch looking deals, those are like a it's like a on-off switch, a silicone based switch like MOSFET, to turn this part of the circuit off while I do this, and then turn it back on while I do that. And because of all these silicone switches, that causes parasitic draws and this and that and the other, and they got to accommodate for all that with these resistors and stuff over here. So that a lot of that stuff's just to accommodate for problems in the circuit design. So okay, first off, in the middle here, VM, you got right here is your basically your ground for your oxygen sensor, and it is 1/2 of VCC. Now we're doing 5 volts, right? So half of 5 volts is 2.5 volts. So we have a virtual ground at 2.5 volts. And this is like, you can consider it ground, you can consider it zero as far as it's concerned to this circuit, to the oxygen sensor, 2.5 volts. Now coming off above that 2.5 volts is another 450 volts, 450 millivolts above the 2.5, so 2.95, and this goes up here and is compared against the voltage output of the nurse cell. When the nurse cell is being fed 20 microamps, the resulting voltage is being compared to 450 millivolts above ground, and if that's like the target, that means it's at perfect lambda when it's at that 450 millivolts. And if it's above or below, this pump current circuit is going to put out current, not voltage but current, at all the way down here at IA, and it's feeding current based on whatever this reading is, and it'll put out a negative or a positive. negative or positive current, depending on the comparison of the 450 millivolts to the nurse cell. And so that current that it puts out in here and is using to run this is what you measure to get your output. Now what they do is they got a buffered current sensor, and that current sensor, they have two settings, multiplied by or gain of 17 or a gain of 8, and then their gain of their opamp is so bad that they gotta really accommodate the numbers, because it doesn't amplify that linearly or something. I don't know what they're up to with this. And so my circuit is gonna, I got this idea to do away with this whole side of it. I'm gonna do away with this whole side of it. I see now what they're doing is they got this op amp up here running this pump current side of it, and they're doing that, and that's all analog, just doing its thing, right? Now the next side of it, okay, the 450 millivolts, so you're feeding this 20 microamps, and then you're comparing it to the 450 millivolts, and the results are being pumped into this other side, right, in a current form, and then you're reading the current used for that with this, and that's your output, right? Well, up here is what you're doing is you're making it to read the temperature of the unit is done off the nurse cell, and to do that you're pumping in an AC voltage, very low current, through this nurse cell and reading the voltage drop as it goes through. And your target temperature of this whole system is when this nurse cell has 300 ohms of AC resistance, right? Now what they're doing is they're switching one off while they do one thing and switching another on when they do another thing, and that's why they got a sinking capacitor here to get rid of any AC and stabilize this, and they're using a filter to, you know, because this thing is going to put out kind of a bouncing, I've seen somebody's oscilloscope readings, and it's like a really bouncing signal. So they're smoothing it out and then using this to put out the current based on that. But what they're doing is they're shutting this whole system off, they're running some AC voltage through it, and that goes through and to this weird switching thing, and it's perfect timing, I guess. And then they're reading that voltage, or the resistance, the AC resistance or reactance, I guess it would be called, of the nurse cell. They're reading that, and it's putting out here, and your target resistance for perfect lambda, for actually utilizing this and getting a correct reading. To get a correct reading out of this, it needs to have this be at the temperature to where this is 300 ohms in AC resistance. And I'll show you where it says that and all that, but that's the thing. So you got a couple things going on this nurse side of it. You're reading the difference. You're feeding in the 20 microamps. You're reading the difference of that to the 450 and pumping in compared to that, and then you're also pushing in AC voltage and reading the AC resistance. So if we look at this, you got 100 nano capacitor, and then because this is LSU 4.2 and 4.9, so what's used for the 4.9 is on the right. So you'd have a 300 ohm resistor here, 301, you probably never fired a 301, but a 300 here, and then this was a 31.6 kiloohm and a 100 nanofarad capacitor, and that's what's used to pump the AC through here and read the voltage drop from doing that. So you get your 61.9 here in between these two, and that's going to be, like I said, like a 100 ohm, I believe, laser trimmed. So you can see right now there's going to be no more than 600 millivolts going through this side, or minus 600 millivolts. And then there's going to be just that 450 millivolts is going to be the highest it gets over here, and it's super low current. I'll show you that in a minute. So I mean, you can learn a lot from looking at this. And see, I know it's in here somewhere, but I was reading, you know, we got to pump our current, our feed current, our current pump is going to put out to current into here, depending on the difference up here. Well, the most current this thing's going to put out at once is like the limit, the very top limit. I think it said 30 milliamps. I could be wrong about that, but it's something pretty low. You don't want to go like just dumping current into it to make it reach a certain point. It's got a limit, and I'll get to that. But see, if we look at this circuit, and you know the sections, we got your AC side to read the temperature. You got your comparison side to know how much to pump into this side, and then how much you pump into this side is getting read, and that's your output. Now your output from here is going to, let me see some of my other stuff. Was it no, wait, where was it? Oh, it's over here, I bet. Yeah. So you can see a little bit what's going on here, but it's backwards as the other one, and it's kind of confusing because of that. And it's a really lame circuit that doesn't show everything, it don't seem like. But if you go down to this ain't the right one, but this tells you a lot right here. So nominal internal resistance of the nurse cell for new sensors operating calibration point, measured with AC frequency at 1 to 4 kilohertz. 1 to 4 kilohertz AC frequency, it should be 300 ohms to be at the correct temperature. Now, and that is at less than or equal to 250 microamps for that AC frequency. So now that tells you, the thing about these is the closer and more accurate you are to keeping the temperature at this number, is the closer and accurate your sensor output's going to be. You're not going to get an accurate output symbol if you're not at the right temperature. It's just not going to happen. You got to keep, it's real important to keep the temperature at the right spot, and then you'll have the most accurate output from the rest of your circuit. Now, reference pumping current, continuous 20 microamps. I'm sure I've said that already. So your max pumping current into the pump cell, the bottom side of it, is no more than, yeah, it wasn't 30 milliamps, is no more than negative 9 milliamps. Or yeah, it's negative 9 milliamps is the least, the most negative, and then most positive is 6 milliamps. So yeah, those are your max swings of your output, or of your pumping into it, right? That's the max you're going to be pumping into it with this pump current circuit. That's the max you pump into it, negative 9 or positive 6 milliamps. Now this 20 microamps is for the reference pump. See, I don't think that has any, I don't think there's any reference pump to this pump side. I think that has to be this right here, which is the reference current to the nurse cell. Sync current or signal current. Yeah, I don't think so. This is really hard to decipher here. It took me a while to figure this out. It took me a while to find this page. Most of them only have this, and they don't have this whole diagram here. So, okay. So where we're at is you measure your current used with this sense, and then they either multiply it by 17 or 18, depending on if you're on the rich setting or the lean setting, and that makes your output that you read. That's what I was looking for before I got sidetracked. So here's the lambda sensor. Yeah, this is it. Okay, so this is the data sheet. Well, this is that data sheet. This is like the what is this called? Technical data sheet, basically. And this is your just regular data sheet. Now, this gives you some of that stuff. Nominal resistance for nurse cell. That means that's the temperature, the output for the temperature at when you're at the right temperature, and your temperature range. Exhaust gas temperature for a short time. Exhaust gas operating temperature. So basically, when it gets to 300 ohms, it's going to be at 930 C, I guess. So I'll give you an idea. If it, even if it ain't right exact, it's give you an idea. Steady state power for the heater. Now you want to be prepared for it to reach up to 15 watts. I read somewhere. Your heater control frequency greater than 100 hertz. There's a max somewhere. I'll find that rating. But okay, heater strategy. See, they're showing 1.5 volts and 8.5 with the ramp up. I couldn't find where I seen the more detailed stuff about that heater strategy, but that might be one of the pages that the links that don't work anymore. So, all right. Well, either way, this page right here shows you what the output's going to be from measuring. You're measuring the current used here across this 6.1 or the 61.9 resistor and the whatever this one is. I'm pretty sure it's 100. Together they're going to draw their current, and you're using the current sense set up here for the output, and that's what this is going to be. Now this current right here, this IP, this is what's actually going to be the current red. This is the current red, and this is what this current red is converted to this lambda, and this lambda is the number you go off of, right? Now on that CJ125, it amplifies. So it amplifies by either 17 or 8. And that's what these numbers are. So if you're making your own circuit, you ignore that. You ignore these two and you go off of these. Now this shows your amperage, signal output, accuracy, blah blah blah. So it does kind of have a two-sided accuracy, and that's why they got two different amplification factors. But you can figure that out. So basically, you're only going to swing no more than 2.25 milliamps basically 2 milliamps positive or negative on your reading right here. Your reading here is going to be reading that there's going to be like 2 milliamps negative or positive going across here is the total of the swing. So now I could get into that. I kind of tried to in my last try at this, where this is your current sense circuit, and you know, well, this is a typical one, but if you notice that whatever's going through there is going to go through these resistors to ground, and you don't want that. So you want a buffered kind, a buffered version. Now, a buffered version of the current sense, and then you get, you know, and see all these resistors got to be the same, like 10 kiloohms, and this one is your adjustment. This will amplify. This is how you amplify the adjust the amplification. And I was going to tell you a little trick on, instead of having this one right here, see it says voltage reference, and this one just goes to ground. Well, if you made that higher than ground and calculated out what your resistance would be, because you know it's going to go negative and positive, right? Because of the setup, it's going to be negative and positive. If this were to go to ground, and I'm not sure if that's ground or if that goes to the floating ground, which, or the virtual ground, which is 2.5, I'm not sure. But either way, I figured out on like a year ago when I was looking at stuff, I could make this like 2 volts, because I know it's never going to be 2.5 is the middle point, and I know it's only going to swing by just a small amount, right? So if I put, instead of putting ground here, if I put 2 volts, this will never actually, I was figuring it out somehow to where I could calculate it and not put ground here, but put like 2 volts or something below where it would ever swing negative, and then I could do that and I would never have to deal with a negative number. I just calculate it out. But there's even an easier way. Now if you look at this, see, I don't want an analog op-amp here dealing with this, because you know, when I got this AC going through here to measure that, you know, that the here, let me show you a picture of that so I can you can better see it. And that is in, what was it, this one? No, I guess it's got to be this one. Let me see. Oh yeah, I'm giving you this link because this guy's box here has these nice little diagrams here that shows you stuff. But I mean, he does some things different than anybody else, so you gotta be careful. You can't follow everything in here just completely. But he gives you equations for the pump voltage around the loop. He talks about a lot of interesting stuff. But here's the circuit for the AC. Now obviously this should be 100 nanofarads, and he's using 1 microfarad, or yeah, whatever. But he's using a different setup, so you gotta be careful about that. And that's 10K. We need to use what the datasheet said, which was, what is it, 31.6K. So he's basically, he's got the 10K because his setup's running a LSU 4.2. You gotta realize that. But the design of this circuit shows you push your AC signal through the limiting resistor that limits the current, and through the capacitor that blocks the DC, and it goes through your cell, and then you read it. See, I don't know why he's got it like this. It should not be connected right there, I don't think. So yeah, it's got to go through the thing first, and then you read it. So you got to read the voltage drop of the AC to know the resistance of the nurse cell in AC resistance. And then this capacitor blocks the AC, or blocks DC from coming in, so you're only reading the AC signal. And then you And yeah, and you read the AC signal, and however much the voltage drop was, you know, is your resistance of your nurse cell to get your temperature. So that, but now you gotta realize, okay, we gotta get an AC signal, and we got 2.5 volts is our virtual ground. So that means if you just took a 5 volt signal, PWM at 50%, so it's high 5 volts, low 0 volts, because we got a 2.5 as the virtual ground. You take the 5 volts and 0 volts PWM and push it through this capacitor, then you got an AC signal. It's that simple. You got a simple AC signal just like that by PWM 5 volts through the capacitor, and this capacitor will block DC, so the only thing getting through is AC. And then you read the resistance of the voltage drop, and you know, simple. That's the way to do that. I don't know about any of the rest of his cell, but or of his circuit, but this showed this part good, and you wouldn't read it except after it went through the nurse cell. I don't know why this is here, but yeah, you read what comes through the cell after it comes through the cell to know the voltage drop. I don't know about any of his other circuits. It's all kind of weird, and because he does some weird things, but he tells you, he talks about all this stuff, and it's interesting to read it, and what he says about things. Some of his circuits might be useful, diagrams might be useful to you, but what he says is pretty useful if you're trying to understand this stuff. I don't see anything else that, but yeah, you need to have a very precise voltage sources, you know, and especially your 2.5 for your floating ground has got to be, it's got to be precise, you know, as precise as you can do it, whatever you got to do. I'm not going to suggest anyway, but I got ways of doing it myself. But yeah, this is the calculations for the PID loop, if you're doing it that way. So okay, this is, you know, this is just info resources here. Now this right here, wait a second, right here, this link, I'm gonna leave all these links in the description. So this right here is a, I guess, a controller or just a gauge, but I saved this specifically because, yeah, this is some kind of gauge and stuff, but I saved it just for this, these charts here. So the lambda number value, and this shows how it corresponds to the ratio. And then 14.7 is the ratio for gasoline's, they call it a stoic. I never had to pronounce it before. I read it, but stoic number is like the perfect number for it. It's called stoic or something like that. It's kind of written like that. I don't know if that's how it's pronounced, but but yeah, the 1 is the perfect point, 14.7. So if you're looking at running your car, the 14.7 perfect target fuel ratio right here, but best economy is a little leaner at this, right about here, best power over here, and then you can see your exhaust emissions are going to change with those values. But this chart gives you an idea of where you want to, you know, because you might want to have a power and economy setting, you know, on your setup. I don't know, depends on what you're doing. So this is some resources for that, and I should have something else for that too. Well, no, not for the ratio, but for the lambda is was it this one? No. Oh, dang it. It was this one. Yeah, this is the regular data sheet. Now that gives you the current reading to lambda numbers, and I guess you gotta use. See, I had this other thing, but I realized it was wrong. You gotta be careful reading this stuff because people do things their own way, and then you don't know if it's the right way or not. But here's a table to take that lambda number and turn it to a ratio. There's a calculation for that, but it's nice to have this graph right here to mess with. Now, what I was thinking, okay, yeah, now to get to where I'll talk about that in a little bit, but to get to what I was getting at here, so what you're doing is you're comparing, you're dumping 20 microamps through here, and whatever voltage that creates is compared to this 450 millivolts, and that determines how much current you pump into the pump side, right? And then the current used by the pump side going through these resistors is what you measure for your output of the sensor. Now wait a minute. Now I was thinking, instead of using this analog way of doing a current pump where it's just doing its thing all the time on its own, instead of doing that, I was going to take my microcontroller, an STM32 blue pill, which takes analog reads. If you got the right board firmware added to the Arduino IDE, you can get analog read speeds of 166,000 reads per second with a blue pill STM, whereas 166,000 reads a second, 166K, whereas with an Arduino or an ESP32, and that's at 12 bits, Arduino and ESP32, they're limited to like 15K, and I just could not find a way to get any faster read speeds out of an ESP32. It's pretty slow on the read speeds, and it's known to be a little bit inaccuracy in its 12-bit ADC. It's less accurate. So I'm going with the STM32, and it's got a nice accurate 12-bit, and it's got fast read speeds, and that depends on what what firmware for the board you use. And I made a video about that here on my YouTube account. Let me see if I can find it. I'll show you. I did a whole thing on which one does the fastest read speeds for STM32. Let me see if I can find it. Alright, yeah, this one right here, STM32 Arduino IDE fastest analog read speeds, and I'll show you which board firmware allows the fastest, and it's a big difference. So you got to do it right if you want to get them fast switching going on. So yeah, if you look this one up in my thing, you'll find it. Alright, now so you're feeding the current into here, but I was wanting to take the readings, I was wanting to analog read off of this difference and then filter out that reading, because it's going to be real bouncy and all kinds of crap, and you might have your AC signal going I was going to filter that digitally with the programming, and then have the microcontroller just use a regular digital analog converter to put out and control an output of current on this side. So make it not analog, but read it with the ADC of the microcontroller, filter it with coding, and then put out the correct current that associates with that over here, right? And that's what I was going to do. And then I realized, well, wait a minute, if I'm controlling the current output with the microcontroller, then why do I need to read the current used with this section here? So I could do away with this whole section of this current sense section, because I already know what current I'm giving it, so there's no reason to sense it, you know what I mean? So you can do away with this whole side of this shits if you just measure this voltage comparator, and you measure off of here the difference, and you use some coding to filter out like your AC pulse and any, you know, it's going to be bouncing up and down like super high frequency, and that's why they got this filter circuit here to help stabilize that down and average it out, you know. Well, you just do that with code. You average it out with your code, you remove any other signals that don't correspond to that, like your AC, and average it out, and then you just use a digital analog converter and a little circuit to feed the current into this side, and then you know what current you're feeding, so you don't even need this whole side of it. That's the little trick there, because I had tricks to doing this and I didn't realize, well, if I control the current that's going here digitally, instead of having this just feed it on its own, this opamp just feed it on its own, if I'm controlling this digitally, the current going there, then I don't even need this whole section. You will have to figure it, because it's all based on the current going through these two resistors, so you'd have to calculate it, what it is concerning those two resistors. It's not the exact current you're putting out here, it's the exact current that's going through these two resistors alone. So you got to make sure you realize that, and then you can fucking get rid of this whole thing, this whole side of it, and you're just down to this part being important and your temperature part being important, and knowing how to calculate the output of this to put out the correct current, and how to know how to calculate that current used to what you need for to know your output altogether, which is these numbers here, because you're only swinging a little bit here. So that's the little trick to it. I hope somebody can understand this. I mean, if you can't understand what I'm saying, I don't think you're going to get it anyways. You know, so I guess, you know, if you gotta look. See, I just looked at this and back engineered it. That's all I did. And then I took all this other resources I found, and they helped me out. Now, like, which one was it? This one? No, this one. Okay, this guy's circuit here. I mean, that helped me out reading all this stuff, and a lot. Helped me out a lot, really. But if you can't figure all this out, you know, this, okay, I don't think I said that yet. You have to use what are called zero drift op amps. So, you know, this is all going to be done by op amps and digital to analog converter and your microcontroller. So if it's all done by that, then so you got your 2.5 volts for your virtual ground, that's got to be precise. Then you got your 450 millivolts plus that virtual ground, and that's got to be precise. And then you got your op amps and your pulse, and that's just going to be a PWM signal through the resistor and all that. You should know how to measure that. So you're only going to use op amps in a digital analog converter, right? Now, what most hobbyists, electronics hobbyists, don't realize, because you never have projects that really need to know that, but the volt, you know, say you got this in a car, say it's in a drag car, and you're at the drag strip. It's going to get super hot, and most people don't realize, electronics hobbyists don't realize that the temperature affects op amps really strongly, way more than you expect. That affects their accuracy and their output way more than you expect, way more. So you got to use what's called a low drift or zero drift op amps, and what that means is, as the temperature changes, the drift of the offset drifts change very smallly, way less than your general op amp is going to have a wide swing determined on compared to what the temperature is. And the zero drift is about the best you can get. They cost a little more, quite a bit more actually, and it's hard to find good ones for cheap. You gotta really watch the numbers on them, because sometimes they kind of trick you. Sometimes they'll have super low current output, and sometimes they'll have only 1 volt fucking supply out, or 1 volt output operate. You know, they have low op. Basically, what they could do is detune a regular op amp and call it a zero drift. So you gotta really look at the data sheet to make sure it reaches what you need, the current output you need, and the voltage you need. Well, these are the ones I could find that were the cheapest on eBay that met what I needed. And I got the 8629, which is the dual version, and it has an current output of like 15 milliamps or something, and it's a 5 volt op amp, and it's got the zero drift. And it's made for like strain gauge sensors and stuff that's really small voltages and precision, you know what I mean? And so you gotta really look at the ratings on these things, because they're a little, you'll get tricked with some of these people trying to sell zero drift op amps, and some of them get real expensive. You could end up paying $4 for a stupid op amp, you know. So these were the cheapest I could find on eBay, and that was like a year ago. I don't know what they got now, but so that being said, these, you know, you gotta know that there's a big swing with the temperature if it's not a zero drift, and hopefully you can figure it out from here. I ignored a lot of this stuff because it has no meaning to us if we're making a custom circuit. So I just ignored everything about that doesn't apply to the custom circuit. And you can get a lot of information and understanding from reading through all this crap, and how they do it and stuff. But yeah, they're going to make it kind of confusing to you, so you can't figure it out. You can't back engineer it like I did. It took a lot of work and thought and wrap my mind around it to figure this out. And so, alright, now, say you don't understand a damn thing I'm saying, you tried and you can't figure it out. Well, see, now this guy sells this thing. If somebody was selling or showing a design or selling it, I don't remember which, and they got, for the CJ125 chip, you know, just a board for it. And the CJ125 chip, this Byland Lambda shield, they make it a shield for an Arduino. It's a Lambda shield for an Arduino, right? And then these GitHub thing, here's all the codes, right? And this is the only way I could find these damn codes to communicate with the CJ125 chip. is in this guy's code here, because I couldn't find them anywhere. It's weird, they're not available or something. So so these codes are how you communicate with the chip and change its settings and stuff. And then pin assignment, serial rate, and then this is the table, conversion table for converting the readings to the lambda number. And you got to remember that they, you know, with the CJ125 chip, they're multiplying the reading using that current sense opamp, either by 17 or 8, depending on what you got set on. And this is the oxygen conversion. I'm not sure what that is about. But yeah, you can utilize either buy the Lambda Shield or Arduino Lambda Shield, or you can just make your own circuit board and utilize some coding off of this and understanding off of this. But you can learn some stuff just by reading this, you know, and see how they did it. And yeah, you'll get some understanding from this too, and you should be able to find this Arduino Lambda Shield somewhere. Somebody's got to be making one. Lambda Shield for an Arduino. If you look up Byland, I'm sure you can find it. But yeah, you know, I mean, if you don't want to make your own circuit, and it requires, well, it's not that hard to chip. Well, you gotta, yeah, it's not that hard to chip to solder though. But yeah, because yeah, if you can't figure it out yourself, you can look towards this direction. You know, they might be still making these. I don't know. It's been a while. But hopefully I explained it all. Yeah, I made a whole video on this earlier, and I realized I was misspoke a lot, and then part of it I forgot how it worked, and I had to redo this video, and now I don't know if some of the things I said were in that video or I forgot to say them in this video or what. So hopefully I didn't miss covering certain part of it. But this info here will all be in the description, and they'll help you out. All right, later.